In a stereo echo effect, the repetitions of our signal occur at different places across the stereo field. Even if our dry, unprocessed signal is in the center, we might have the delayed repetitions that occur on the left or also on the right. In order to create the effect, we're going to put together some of the ideas about how we delay a signal in time and incorporate some of the concepts with how we perform stereo processing. One special type of stereo echo effect is the ping-pong delay. In this case, the repetitions of our signal are going to follow a pattern where they alternate between the left side and the right side. So let's jump into MATLAB and look at how we can implement a couple different types of stereo echo effects. Here in MATLAB, I'm going to demonstrate two different examples for creating stereo echo effects. The first example will be based on a basic feed-forward echo. I'll be expanding upon the multi-tap echo we created previously. In the multi-tap echo, we use multiple delay blocks. That's helpful for us here because we're going to use one delay block for the left side and another delay block for the right side. So rather than rewrite all the code, let's copy and paste over some of the stuff we created previously. We're going to import in the same example test file and then add on some zeros just for an extra tail at the end of our sound file. We'll also want to have this tempo synchronized. Let's copy and paste this part over. And for this example, instead of using a quarter note as our shortest delay, let's use an eighth note. That'll be what happens on the left side. We use D1 for the delay that's on the left and D2 for the delay that's on the right. So now our right delay, D2, will actually end up being a quarter note. Another thing that we can do is copy over this command where we initialize our output. For our output, it's going to be a little bit different. Instead of being a mono one-channel signal, it's actually going to end up being a two-channel stereo signal. So we need two columns, one for the left and one for the right. We'll initialize it already as a stereo. Then I'm going to come back over here and make use of this approach called array indexing. This is when what we do is index an element that's in the past, a previous sample of our input signal, in order to create the delay. So we'll have two separate gains. How about we have gain 1 for the left side and gain 2 for our right side? Something a little bit less, 0.3. All right, then we'll go through a loop and go through sample by sample through our input signal in order to create our output signal. It's going to be a little bit more complicated than before, where we just had a single channel that we were trying to create. We're still going to set it up with conditional statements for when we want to have a delay and when we don't. So initially, before we have the element in our array that corresponds to having a delay, we want to just add in zeros. So it's true, we want to have on our left side, channel 1, and have our input plus 0. We also want to have a second channel. This will be our right side, channel 2 here. And in this case, because we're setting up a stereo signal, we actually want to reduce the amplitude for our input. That way, it's not too loud on both sides. When we create a stereo signal and something's panned to the center, we multiply by 0.707. So for something panned to the center, we need to have this multiplication done to our input. So this takes care of when our index is less than D1. So that's our first case. Then we need a second case. This is going to be an else if statement for when we want to have a delay on the left, but we're not yet ready to have a delay on the right because D2 is longer than D1. All right, so in this case, what we're going to do is make this an else if. And now on the left side, this is where we want to be able to bring in our indexed version of our input signal. We even have a scalar here that we can use, G1, that we multiply by to bring down this level. But on our right side, we're still just going to be adding in a 0. We're not have anything yet to add in for the delay. Then we get to the last condition, and that's going to be we have two different channels, both getting a delay. So we'll have G2. That's going to be for the right side. It has a different delay time. Then that'll take us through the end of our loop, and we'll be able to create our output signal. So let's listen back to our end result after we do the processing. So now we've successfully created a stereo echo effect with different delays on the left side and the right side. This approach was based on a feed-forward echo, so we only have a single repetition on each side. The second example that I'm going to demonstrate is called the ping-pong echo. And this is where we have an alternating pattern of repetitions that go back and forth between the left side and the right side. We're going to need to use feedback here in order to create the repetitions that go in this pattern. So I've started another script over here. We're going to reuse a lot of the same code, make some important modifications to it. So just like before, we're going to bring in our sound file and calculate the delay time. So let's copy and paste these things over. There is an important modification we're going to make though. Before I set up that there's going to be two different delay times, one for the left and one for the right. The ping-pong echo effect in this implementation, what we're actually going to do is feed the output of delay 1 into the input of delay 2. So we'll actually want to have identical delay length for both sides. So I'm going to change this and have it also equal to D1. In fact, we could just go without this variable, but just to keep them straight that we have two different delay blocks, I'm going to label them with these numbers. So we'll have an 1/8 note delay that happens on the left side, and after it gets delayed on the left side, we'll feed it in to the right side. And then the output of our delay 2 is going to get fed back in to D1. So we want them to each happen right after an 1/8 note. So in this case, I'm not going to use the array indexing approach. Rather, I'm going to use the delay buffer approach. Because what we want to be able to do is feed the output of these buffers to the input of the buffers. So we'll initialize some of these things here before our loop. Have one for D1 and the other one for D2. Now we're ready to go into the loop. So make some space for us. We're going to say, we'll start from our sample number n, goes from 1 to the length of x. And then what we're going to do is calculate some temporary variables that we're going to use for the left side and the right side, or the left channel and the right channel. So I'll call this first variable, this is going to be the signal that's coming out of the left side. So just like before, we want to have a version of our input signal that's been reduced in amplitude for the current time sample. We're going to have the same thing on both sides. So we'll have one for the right channel. Then we're going to add something to it. Here, we're going to add to it our buffer that's used for the left side. So we have buffer 1 that's used for the left. We're going to get the end sample, the last sample out of that buffer. And then we'll have the other one for the right side. So this is what we create for our left and right channels. We can jump ahead quickly to the end here, how we actually create our output. It's going to be where we concatenate these two things together. Our left channel and our right channel, side by side in the two columns. Then we need to figure out how we want to iterate through the delay buffer, where we're going to put in a sample into the buffer and then slide it along each time through. So in this case, we're going to say buffer 1. Here, we're going to create this array. It's going to be our input signal plus the output of buffer 2. This is how we're going to create feedback. the end of buffer 2 gets fed back to the input of buffer 1. We can go through 1 through the end, -1, like this. We want to have a similar thing happen on the right side. So this will be buffer 2, except we only want the input to buffer 2 to be based on the output of buffer 1. This way our input signal, it gets fed into buffer 1 and then it trickles through, and then it will eventually get placed in buffer 2, and then it's going to get trickled through buffer 2 until it gets to the end, and then it gets fed back in here to buffer 1. And we want to ensure that we don't have this infinite feedback kind of occurring, so we'll have a feedback gain. Now, if we wanted to, we could set up different gain amounts. I'm just going to say 0.5, so 6 dB gain reduction, and we'll only apply it here on this final feedback amount. So we'll only reduce the amplitude here when we feed the signal all the way back through the whole system to the beginning again. So now what we can do is wrap up our loop and listen to our output signal. We'll have our signal repetitions bouncing back and forth in this feedback loop and hearing multiple repetitions on each side. Just to make sure that we can hear this, I'm going to go back and say that we want to have our length be a little bit longer this time. More zeros, so the tail lasts for a longer period of time. So this is how we can create 2 different stereo echo effects. The first approach was based on a feed-forward design, and our second example was based on a feedback design to create a more interesting kind of ping-pong echo.